if you have questions about the scoring for that. But in short, there were 3 parts. The multiple choice was worth 30 points, the free response was worth 60 points, and the derivation was worth 10 points. So let me know if you have questions about how I graded that. I can certainly answer those. Oh. Sorry. Alright, so the amount of electric field passing through a surface is called what? Alright, just a few more seconds. I'll stop at 28. Okay, awesome. A is the right answer. Remember, we've really only had a few things, and one of those that we've covered in this chapter, and one of those is the definition of flux. And flux is the area dotted, or the electric field rather, dotted with the area. When I take that dot product, what I'm really saying is the electric field that's perpendicular to the area, and the total flux is going to be the sum of all of that over our surface. So we'll write a little circle there. That just means over a closed surface. The integral over some surface. And that's our definition of our flux. Gauss's law is useful for calculating electric fields that are which of these? Due to point charges, uniform, symmetric, or due to continuous charges? You might not know this right off. Let's see if we covered this. Yeah, actually, I'm not sure I like this question. So why don't we just skip it? Y'all just put A. I'll count that right, okay? So just all, that's not necessarily the answer. There are several answers, but just all put A. Alright. I'm going to stop at 58. Okay. I'm going to count A right, but we're just going to skip this question altogether. Gauss's law applies to which of these? Lines, flat surfaces, spheres only, or closed surfaces? Think back to our flux, what flux means. Lines, flat surfaces, spheres only, or closed surfaces? I'll stop at 30 seconds. 30 seconds. Okay, awesome. D is the right answer. Remember, Gauss's law says that the flux is equal to the charge that's enclosed within our Gaussian surface divided by our permeativity of free space. So that means that Gauss's law is going to apply to these closed surfaces. It only applies if my surface, goes all the way around my charge. And we'll stop there, actually. Yeah, we'll stop there. All right, let's pick up with this example. We've worked on something similar to this, but here I just want to know what is the net electric flux through this surface S, and then I give you the charges Q1, Q2, Q3, Q4, and Q5. Notice that Q1 and Q4 are both positive 3.1 nanocoulombs. Q3 is negative 3.1 nanocoulombs, and Q2 and Q5 are negative 5.9 nanocoulombs. So I want you to calculate what is the electric flux through that surface S. Another minute, get a little head start. All right. So remember our Gauss's law says that the total flux is equal to my enclosed charge divided by my epsilon naught. And so each of these charges will contribute to that flux. But these two charges will not contribute to that flux at all because these are not enclosed within that Gaussian surface. So I only have three charges here, Q1, Q2, and Q3 that are contributing to the flux. Now, a couple of these charges have flux going in and flux going out, and we can just cancel them out. Right? We can cancel out the flux due to this one and due to this one. I'll go ahead and just sort of calculate it with them in there, but we could just ignore those charges altogether. Let me just show you what I mean. So here we have our Q enclosed. That's going to be plus 3.1 nanocoulombs. I'll go and write it in coulombs, our SI units, which you'll need to do. 10 to the minus 9 coulombs, minus 5.9 times 10 to the minus 9, minus 3.1 times 10 to the minus 9. So I can just add those charges up arithmetically. They're not vectors or anything. And then just divide by my epsilon naught, which is 8.85 times 10 to the minus 12. These two cancel, and I'm left with, let's see, what am I left with? I get 670. Is that what y'all got? Yeah, so I get 670, and this is actually negative 670. And let's see, this is, remember our units here are electric field times area. So my units are going to be electric field, which is newtons per coulomb, times meters squared. Those are my units for flux. Okay? Just applying Gauss's law there, remembering that if I have equal and opposite charges, I can just forget about those altogether, because whatever field lines are going to go out are also going to come in, and then those will negate themselves. All right, what is the charge enclosed by the cube in the previous problem? This was back a few pages. Where was it? Oh yeah, this problem. So here I had this cube, and we found the flux on the top left and right faces, and now we want to know what is the charge enclosed by that cube. So now we'll also need to find what is the flux through the bottom, front, and rear faces. So let's try that out. I'm going to sketch it out here. I had this cube. It was sitting, I think, at what, x equal 1 to x equal 3, if I'm not mistaken. Is that right? Yeah, so it went from x equal 1 to x equal 3. That's the bottom of it. And then it went up to z equal 2. Sorry, my 3D figures are not real great. That's okay. And then our flux values that we got before, we found that our total flux from the top was 16 Newton meters squared per Coulomb. Remember, electric field times area. Over here, my electric flux was negative 12 Newton meters squared per Coulomb. So actually, if I wanted to draw this correctly, I'd draw it into the area. And then over here, I had 36 Newton meters squared per Coulomb. Just to remind you, can somebody tell me what that electric field was, the electric field vector from that previous page?
3x plus 4j.
Okay, so that's my electric field. It's dependent upon x, so as x increases, the x component of that electric field will also increase. That's in newtons per coulomb. So now I want to go through that same exercise, finding the bottom, the front, and the back, the bottom, front, and the back flux values for this cube. Now some of these are going to go to 0. Can you think about which one of these will go to 0? Will it be the bottom, the front, or the back? The front and the back. Why is it going to go to 0? There's no case. So if we think about this, the front and the back, for the front and the back, remember our flux is going to be E dot dA. For the front and the back, my area vector is going to be in the k direction. So for the front and the back, this area vector is in either the plus or minus k direction, because remember the area vector is always orthogonal or perpendicular to the face that you're looking at. Okay? So both for the front and the back, this electric flux is going to be equal to 0. Again, let me say that again. The front and the back, the area vector is in the k direction. It's either in the plus or minus z direction. We call that the k. And whenever I take a dot product, if I have dissimilar terms, like I dot k or j dot k, those are going to be equal to 0. And we're going back to our dot product because our dot product is going to be I, k, cosine theta. The angle theta between I and k is 90. Cosine of 90 is 0. Okay, dokie? So really all we have to do here is find the flux for the bottom face, and that flux is going to be the integral of E dot dA. Give that a go. You have the E here, our area. Remember these, if you remember back from that problem, this is a 2-meter cube, so it's 2 by 2 by 2. So what is the flux along the bottom, or from the bottom of this this cube? What is the flux? Then calculate what that flux should be. Okay, first thing you want to do here is write out, we have 3x I plus 4j. And then you want to ask yourself, gosh, what is the direction of my area vector? What is the direction of it along the bottom? Negative what? It's in the negative j direction, right? This is our j axis. This is our I axis. This is our k axis. My area vector on the bottom is going to be in that direction, which is in the negative j. So I can put this, take away now the vector notation for dA, and instead put a unit vector there. So dA is going to be in the j direction. And then I can do this dot product. I have 3xi dot daj. Remember, I dot j is equal to 0. And then I have 4 times dA. J dot j is equal to 1. So that's going to be the integral of 4 dA. Just take that 4 out. Oh, it's also in the negative j direction, sorry. So I'm going to have a negative there as well. So I have negative 4 times the integral of dA. The integral of dA is just the area of that face, which is going to be 4 square meters. So this is going to be negative 4 times 4 meters squared, which is negative 16. It's negative 16 newtons per coulomb meter squared. Okay, so now we can figure out what is the total flux. We do that just by adding up all these values. So my total flux is the flux for the top, the flux for the bottom, flux for the left, the flux for the right, the flux for the front and back. So we've already found some of these go to 0 because our area vectors are in the k direction. That was the, what was it, the front and the back, right? So these both go to 0, and then I have values for all these. Let's just put those in. Top was 16, positive 16. Bottom is what we found here, negative 16. Left is negative 12. And right is 36. So if I add up all those, I get 36 minus 12, or 24. Yeah, 24 Newton meters per Coulomb. Newton meters squared per Coulomb. That's our total flux. And then I can find, pretty simply now, just through Gauss's law, we can find our total charge. So our total flux is equal to Q enclosed divided by epsilon naught. So if I want to know Q enclosed, it's going to be that 24 times epsilon naught. And that gives me 2.1 times 10 to the minus 10 coulombs. Listen, this is really the only type of problem that we've encountered in this chapter, so you'll certainly see that, a problem on the next test where you have a free response problem, where one, you have to find the flux. I'll give you a electric field vector in IJK notation, and I'll give you some regular object like this where you have to find the area vectors and then calculate what is the flux through those spaces of whatever surface it is. It might be a cube, but it could be something else, like a cylinder or a sphere or something. And then you have to apply Gauss's law in order to find that. So this, you'll certainly see this on the next test. All right. There are a couple of different variations of this in the homework, so I'd recommend that you go through and look at that. Make sure that you're up on that. Gauss's law might seem a little foreign to some of you because it's sort of new, but it's actually pretty simple once you get the hang of it. There aren't that many steps to it, to actually applying it, but it's just sort of wrapping your head around these new things and some of the things that are old that we haven't seen in a while. There's one other thing that you'll need to know, and that's just how to find Coulomb's law from Gauss's law. I don't usually do derivations on the test, but you could see this on the next test, okay? So it's not going to be a take-home derivation, but you could see this. You will have a take-home derivation, but this won't be it. But you do need to be able to derive Coulomb's law from Gauss's law. Let me show you. Gauss's law says that the flux, let me write it out, it says that the flux is equal to the enclosed charge divided by the permeativity of free space, that constant. Remember, the flux is the integral of E dot dA. I can multiply both sides by epsilon naught. And I'm going to take my electric field out. I'm assuming here that my electric field is perpendicular to my area. If I imagine that I have this charge over here, a positive charge, let's imagine a spherical surface, spherical Gaussian surface. Is it AU or UA? I don't know, I think it's AU. Yeah, that's right. All right, so if I have a spherical Gaussian surface, then what is the area of a sphere? No, not 2 pi, it's
4/3.
no, you're thinking volume. 4/3 is what was it, Shane? You said it. 4 pi r squared. Yeah, we'll all get it. If we all work together, we'll get it. Yeah, it's on your equation sheet. So if you don't remember, that's fine. Just look on there. So the area, the surface area, is equal to 4 pi r squared. So when I integrate over this Gaussian surface, I can just replace this with 4 pi r squared. So I get epsilon naught E 4 pi r squared is equal to my enclosed charge. And then I solve this for E, and I get 1 over 4 pi epsilon naught times Q over R squared. And that is our definition of electric field. In fact, this whole thing right here is just K. All right, so not really much to this derivation. Once you start with this, really all you have to realize is that this is for our 4 pi r squared. But otherwise, it's really just Gauss's. Okay, so you should be able to do that. It won't be many points on the test, but if you have it, it'll probably be, a 5-point sort of quick response. And then that's all that chapter for that test. Again, look back through your homework. As you saw in the last test, we had several problems that were pretty close from the homework, so make sure that you're up on the homework for this chapter as well. It's really more of the same of what we've done, but like I said, practice always makes the key things better. Questions, John? No? Okay, well, let's move on to the next chapter. I think that's right, that was in here. Yeah, so these are all homework things. Again, things that are very similar to what you've seen already. These are probably some of the harder chapters. As we get into some of the later stuff in LRC circuits, AC circuits later in the semester, those can be kind of difficult because we'll see some simple differential equations, which is stuff that you probably haven't seen before, and some integrals that we haven't seen before. But this stuff I find is sort of the conceptually most difficult, the idea of potential and fields and energy, potential energy. So just sort of buckle down right now and try to push on through with this chapter. And then once we get into chapters 3, 4, and 5, I think that you'll find that those are a lot more simple. But this one, just conceptually, is kind of difficult, I think. So we're going to look at potential difference and electric potential. First of all, remember we had a couple things. We had Coulomb's law, which was forces, which dealt with electric forces. And then we had electric fields, and that dealt with our electric field was a force per unit charge, or F over Q. And now we're going to deal with potential, which we're going to call V, and this is going to be an energy per unit charge. So Coulomb's law describes the force, electric fields describe the force per unit charge, and potential will describe the energy per unit charge. You could see some multiple choice questions just asking you to clarify between those different things. But potential, remember, is our energy per unit charge. Fields is force per unit charge, and Coulomb's law is force. These all look a lot alike too, unfortunately, so they're kind of difficult to keep separate. They look alike because they all go back to Coulomb's law, but just to remind you, our Coulomb's law was KQQ over R squared, electric field was KQ over R squared, and now our potential, due to a point source anyway, will be KQ over R. We'll also see in this chapter, just go ahead and warn you of this, we'll see potential energy, which is going to be different from potential. It'll just be the energy of a collection of charges. We're going to call that U, and it's going to be equal to KQQ over R. All these equations are in your equation sheet, but I know when I was a student first learning these, it was kind of difficult to keep them all separate because they all look very similar. And so just, take a little time to just familiarize yourself with them. And of course, as you're working through the homework, that'll help too. We've already seen a lot of these too, because a lot of these will look similar to what we saw with gravitational potential and gravitational potential energy. Okay? All right. Well, first of all, electric forces are conservative. Do you remember what conservative means? It's not like a political thing like Fox News or whatever, or Bobby Jindal, but what does conservative mean when we're talking about forces? Conserve something, what does it conserve? Energy, right. So conservative forces conserve energy. And only certain types of forces conserve energy. Those are only certain types of forces are conservative forces. Y'all remember the type of forces, sort of a broad class of forces that is conservative? Okay, gravitational forces are conservative. Field forces are always conservative. And field forces are conservative because they don't require contact. Anytime you have contact between two surfaces, you're going to lose energy. Because of friction, and they exchange heat, or they produce heat. So field forces are conservative. Gravitational forces and electric forces, as far as we're concerned. There are some nuclear forces that are also conservative, but we won't deal with those. Let's see. The conservative force is also path independent. That means that the amount of work that it does is not dependent upon the path. We'll see that in just a bit. If you remember from last semester to conservative, let's see, we already wrote this, but it conserves energy. The amount of work done by the force changes the energy by the same amount. So when we're talking about gravitational forces, this object has a gravitational force acting on it. If I let go of this object, it'll fall. And as it falls through space, the gravitational force is acting on it over a certain distance. When it goes through a certain distance, it will have a kinetic energy that's equal to the amount of work that's done by that gravitational force. That's what it means to be conservative. Any work that's done by the force is transferred directly into energy on the object. There's no energy lost. Energy is conserved. And non-conservative doesn't conserve energy. And friction is an example. We had questions like this last semester, but you could see them again, just sort of distinguishing between conservative and non-conservative forces. The work done by conservative forces is path independent, and the work done by non-conservative forces is path dependent. A good example of this is if you go down a slide or if you jump off. So say both of these guys start right here. One guy has conservative and non-conservative forces acting on him. Right, the conservative forces are the gravitational forces. The non-conservative forces are the frictional forces, or that would be the kinetic frictional forces. And the other guy only has a conservative force acting on him. All right, as this guy drops down, this guy over here, the amount of work done by the gravitational force, which is his weight, mg, times his height, that is all converted into kinetic energy without any loss at all. However, this guy over here, the amount of work that's done on him is equal to that mg times h minus the work that's being done on him by friction. And so when I say that they're path dependent versus path independent, imagine that if this guy took a different path, say he took a path like this, after which path would he be going faster at the bottom of the slide? Would he be going faster on the red side after he traveled that distance, or would he be going faster on the black side? Which path would he be going faster on? The black side, right? Because it's a shorter distance, he's losing less energy due to the frictional forces. I think y'all got this right. We did this last week. You good with that? Okay. Make sure you understand conservative versus non-conservative forces. You could see some problems related to that. So this is our, I think we're just going to skip this little part. Yeah, let's not worry about this at all right now, okay? So we can say that our change in potential energy of an object is equal to the negative of the work when it goes from point A to point B. And so we can also extend this to the electric field, where we have, this is negative F times my change in my displacement. And when I have the electric field, I can say that that force is negative QE times delta X. This is just our definition of the electric field. And this only applies when the electric field is constant, which will always be the case for us. We'll see in the end of this chapter what happens when our electric field varies, and there's some cool things that come up with that, but we'll see that in later in the chapter. And we're going to skip this little aside as well. Okay, so imagine this. I have these two plates. I have a plate that's positively charged over here, and a plate that's negatively charged over here. It's going to happen to be, we'll see this a little later, but on this side, on the left side, this is our high potential, and this is our low potential. We'll see that a little bit later and how we define what these plates are. But this is our high, remember potential is energy per charge. So over here, I have a lot of energy per unit charge. Over here, I have a little bit of energy per charge. These are positive charges lined up along this plate. They're negative charges lined up along this plate. This is a capacitor, which we'll get to in the second part of this chapter. But right now, we're just imagining them as two separate plates with positive charges on this side and negative charges on this side. High potential on the left, low potential on the right. So here, if I move an object, a positive charge, and I move it to the left in this direction, has the electric field done positive or negative work on that positive charge? Let's try that as a clicker question. So has it done positive work? That'll be A. Or has it done negative work? Is that B? Has the electric field done positive or negative work? And remember, go back to our definition of the dot product. Work is force F dot E. Not on there in the same direction. If they're opposite directions, if they're perpendicular, what happens? So has the electric field done A, positive, or B, negative work on this positive charge? All right, I'll stop at, say, 40 seconds. 40. All right, so remember, y'all, that our work is equal to the dot product F dot D. So in order for us to have positive work, F and D have to be in the same direction. Remember, because our dot product is going to be FD cosine theta. In order for this term to be positive 1, theta has to be 0. That means that the two vectors have to be in the same direction. If they're in opposite directions, theta is 180, and that's going to be negative work. If they're perpendicular to one another, theta is 90, and that's going to be equal to 0. So here my work is positive. A is the right answer. Because the force and the displacement are in the same direction. Has the potential energy of this positive charge increased or decreased? Is it A, increased, or B, decreased? Think about the potential energy. This thing is moving from a high potential to a low potential. Has the potential energy of this positive charge, has it increased or decreased? All right, I'll stop at 25. Okay, awesome. B is right. Sort of led y'all into that. So I'm moving from high potential, high energy per charge, to low potential, low energy per charge. And so I can imagine about the potential energy has decreased. That is the right answer. Let's see. I have a friend. This friend's name is Power, and he's just been really stressed at work lately. Y'all know why? Because his boss has been making him work overtime. Power is work overtime. You get it? Yeah, you get it, but it's not that funny. Is that the thing? Yeah, I thought it was a little bit funny. Okay, so if positive work has been done on the charge and the potential energy is decreased, we have had positive work. The change in potential energy has been less than 0. So where has that energy gone? What's happened to it? What's that? Right, it turned into kinetic energy. So any of the work that's been done here has turned into kinetic energy. In particular, our change in kinetic energy here is going to be the negative of our change in potential energy, because it's decreased. This value is negative, so we take the negative of it, which is going to be 1/2 mv squared. So if the charge has lost potential energy at point B, its kinetic energy must have increased. Because after all, positive work is being done. And if positive work is done, then the energy has to be increasing in some way. Then we can calculate the charge's velocity at B, at point B. Our change in kinetic energy is equal to our 1/2 mv squared, which is going to be equal to our work done by the force, QE times delta x. All right, this is pretty powerful because this says that you can give a charged particle a particular velocity when it travels through an electric field. We sort of saw this also with one of the questions on the test. It was in the homework as well, but we're going to see it again here. Let's say that I have a proton. It's released at x equal -2 centimeters in an electric field of 1,000 newtons per coulomb. What is its velocity at x equals 8 centimeters? All right, so here I have a certain displacement. My delta x is going to be x final, that's 8 centimeters, minus -2 centimeters. That's 10 centimeters, 0.1 meters. I have an electric field of 1,000 newtons per coulomb. And I have this proton that's released in the electric field. Remember a couple things I know about the proton. I know its charge, which is positive 1.6 times 10 to the minus 19. And I also know the mass of the proton, which is, It's 1.67 times 10 to the minus 27 kilograms. So if I have this proton in this electric field and it travels a certain distance, then I can very reliably describe its velocity. I can come back up here to this derivation that I have for QE delta x. equals 1/2 mv squared. And then I can solve this for v, which is what I'm looking for. 2q delta x over m, the square root of that. All right, and then I can put in my values. I get a velocity here of, let's see, I get 1.4 times 10 to the 5th meters per second. That's a pretty powerful thing, that you can take these charges and give them a particular velocity. And again, we saw that in the first chapter, but we're going to deal with it a little bit more in this chapter. Okay. Let's see here. Why don't we, give me just a second, let me look at your questions here. No, let's wait on this. Pick up this next time. All right, so let's define electric potential difference. The potential difference between 2 points is the energy per charge. Remember, if electric fields is force per unit charge, electric potential is energy per charge. And this is the energy per charge as the charge moves from point A to point B. So if I think about delta V, it's going to be the difference between the potential at point B minus the potential at point A, which is going to be equal to my change in potential energy divided by the charge. The units for potential are a joule per Coulomb, and we call this a volt. It's after Voltaire, so we capitalize it when it's abbreviated. So 1V. You're probably familiar with this. It's the same as we use when we talk about our outlets being at 110 or 120 volts. It's an energy per charge. How much energy per charge do we have? And then also, since I say that delta PE is equal to negative QE times delta X, and here I'm going to put in a little subscript X, because in order for this really to be true, my electric field and my change in displacement have to be in the same direction. We'll see that later. And delta V is delta PE per charge, energy per charge. That's just our definition of what is a change in potential. Then this is equal to negative EX delta X. Then I'll see then that my electric field is negative delta V over delta X. It's just taking these two, and I get an expression for the electric field. Now, for the time being, I just show you this because it gives us an alternate unit for the electric field that is more commonly used. The electric field, we've been using Newton per Coulomb. I think that sort of makes more physical sense, but we can also think of our electric field as being a volt per meter. But later in the chapter, we'll also come to this. We'll see this again, except we'll express this in terms of a partial derivative, where we can determine our electric field based on how our potential changes with space, through space. And we'll deal with that at the end of this chapter and look at it in terms of like a partial derivative. So remember that particles, they tend to let's see, particles tend to lose. Oh, shoot. I'm sorry, guys, I don't have this in my notes. I had taken it out at some point, forgot to take it out of here. So I'm just going to get rid of this and these. But we have these couple of rules that come about when we have positive charges and negative charges when they in either high or low potential. Positive charges tend to accelerate from high to low potential, and negative charges tend to accelerate from low to high potential. You can see some multiple choice questions on your test regarding this, sort of in a conceptual way. If you ever forget it, just imagine your two plates at my high potential, my low potential. This is positive, this is negative. Imagine if I put a positive charge here, it will tend to move in this direction because it's being repelled by the positive and attracted by the negative. Likewise, if I put a negative charge in here, if I put a negative charge here, it's going to be attracted to the positive and repelled from the negative. So you see the positive charges move from high to low, and the negative charges move from low to high potential. Negative charges will tend to move from low energy per charge to high energy per charge. This is useful. We're not going to get too much into this, but it's useful because it allows you to isolate charges and move charges around by setting up a potential in the lab or wherever you are. And I think that maybe when y'all get into PChem, you'll talk more about this as well, about sort of how charges can become trapped in like potential wells. Any of y'all in PChem? Okay, I think that you will get into that when you go into quantum. So we'll just sort of mention it here. Let's do this little quick test. Let's imagine that you have this, correct answers here. But I'll give it to you nonetheless. Did I ever tell y'all that story about Dr. Baker about his test? Did I ever tell you too? Y'all didn't know Dr. Baker, did you? Like the students, I don't think they appreciated him as much as we appreciated him because he was kind of a funny guy and just sort of, he was a good guy. But one time he gave a test and he had bolded all the answers on the test. It was an accident. He didn't mean to do it, but he had given all the answers in bold. And so the students got it, and they weren't sure if he was trying to trick them. Some of them just didn't even really notice, or if he had made a mistake, because he was kind of a tricky guy. You had to watch him. He was always sort of tricking people and stuff. But anyway, that is the correct answer, A. If I have a positive particle and I release it at x equal A, that means at the position x equal A. Now look what I have a graph here with potential on this axis and position on this axis. So what it's saying is if my position is at x equal A, what direction will it move? You need to ask yourself, well, positive particles, what do they move from? High to low or low to high potential? They move from high to low, from the positive side to the negative side, from high to low potential. So if I release a positive particle here, it's going to move to lower potential. That means it's going to move to the left. All right? Because a positive particle will tend to move from high to low potential. So go ahead and put in A. A is the right answer. I'll stop in just a few seconds. Yeah.
When it gets to that first, like, decrease, like, you know, that first minimum.
Right.
Is it going to keep going to the left to get to that lower minimum?
That's a very good question. So that was sort of the next thing. So as this particle comes down here, it's going to come here and it's going to the bottom, right? And then it can't move any lower from this point. This is called a potential well. When it sits somewhere where it can't move any direction because it wants to move to lower potential, but there is no lower potential. What it will do actually is it'll come and it'll sort of come back a little bit, and then it'll oscillate back and forth. So you can get these charged particles within these potential wells, and if they're perturbed a little bit, they just oscillate back and forth. And so when we talk about like the cesium atom, remember the cesium atom was the standard for time, that it oscillates back and forth at a very regular rate. That's what it's doing, that it's inside this potential well, and it wants to move, you know, from high to low or low to high potential, and so, but it can't do that, so it just oscillates back and forth. Likewise, if you had a negative particle up here, it would do a similar thing, because a negative particle wants to move from, low to high potential, but when it's up here, it can't move any higher, and so it'll just sort of oscillate back and forth. I think that was the next question, actually. All right. Well, so the importance of this is that you can isolate particles in a potential well. And that potential well, for example, is if I have a charge right here, we would call this a potential well. it can't get out of that. So you can isolate it and you can hold it in one place, which isn't that easy to do. I think we're out of time now, but y'all have a great day. I'll see you on Wednesday. It's a long week, okay? Y'all try to keep your heads up. Stay focused on what you're doing.